Good evening, ladies and gentlemen. How's everybody tonight? Good. That's good. All right. Well, my name is Mark from the Public Services Office here at JPL. Thank you for attending this May edition of the 2007 Von Karman Lecture Series. In the vast blackness of space, our home planet is a single sparkling oasis of life. Whether the universe harbors other worlds that can support even simple life is a question that has been pondered yet has remained unanswered for over 2,000 years. Over the next 2 decades, NASA will launch a series of spaceborne telescopes that will search for Earth-sized planets around other stars and examine those planets for signs of life. Tonight's talk will explain how we will search for and identify planets that might support life around other stars, and will describe results from the new science of astrobiology that will help us recognize signs of life on these distant worlds. Tonight's speaker is an astrobiologist and planetary research scientist with the Spitzer Space Center at Caltech in Pasadena, California. Having received her PhD in astrophysics from the University of Sydney in 1994, she worked from 1994 to 2004 at the Jet Propulsion Laboratory with research interests that focused on remote sensing observations and modeling of planetary atmospheres. Since 2001, she has been the principal investigator for the Virtual Planetary Laboratory lead team of the NASA Astrobiology Institute, which is a 40-member research team that develops models of different stages of the environment throughout Earth's history, as well as plausible planetary environments for extrasolar terrestrial planets. Just this month, she was selected by NASA to continue her team's research for another 5 years. She has also worked for 8 years as the Solar System Observations Scientist for the Spitzer Science Center, where her research interests focus on acquisition and analysis of observations of planetary atmospheres and surfaces. This research is being used to understand planetary signs of habitability and life for future extrasolar terrestrial planet detection and characterization missions. Please join me in welcoming tonight's guest speaker, Dr. Victoria Meadows.
Okay, hello everybody. Thank you very much for coming. All right, so tonight we're going to be talking about the search for life beyond the solar system. And essentially what we're trying to do here is answer that age-old question, are we alone? And this is the kind of question that we believe has been asked for thousands of years, and probably was one of the first things that when our early tribes people were sitting around their campfires many, many thousands of years ago, probably looked up and looked at the stars and imagined that they were also campfires with other tribes around them. More recently, Giordano Bruno in 1584 wrote this very interesting paragraph, most of which has turned out to have come true. He had no idea at the time he wrote it how prescient he was, but again, it's a very, very interesting paragraph. I'll read it to you. He felt that there are countless suns and countless Earths all rotating around their suns in exactly the same way as the 7 planets in our solar system, and he was correct. We see only the suns because they are the largest bodies and are luminous, but their planets remain invisible to us because they are smaller and non-luminous, also correct. He said the countless worlds in the universe are no worse and no less inhabited than our Earth. We don't know if he's right, but that's basically what we're trying to do right now, to see whether we can prove him right once again. By the way, he was also called a heretic and burned at the stake later on, so he came to a bad end. I've read something of his history, though I felt very sorry for him initially, but apparently he liked provoking people, so he wasn't entirely blameless. So to answer this question of whether we're alone and whether there is life beyond the solar system, we turn to a new science that's probably been around only for about 20 years in full force, and that is the science of astrobiology. And what astrobiology is the scientific study of life in the universe, its past, its present, and its future. And that past, present, future motive translates into 3 major questions. How does life begin and develop? Does life exist elsewhere in the universe right now? And what is life's future on Earth and beyond? What is the future of our own society as our planet and our sun evolves? And to answer these absolutely enormous questions, you need more than one discipline. These are not the sort of questions that can be answered by physicists alone or biologists alone or chemists alone. You need a combination of almost all of the sciences in order to address them. So people who are astrobiologists can come from almost any walk of science. They can be biologists, chemists, geologists, astronomers, planetary scientists, paleontologists, oceanographers, physicists, and mathematicians. And they're all required to work together to answer these questions. But today we're going to concentrate on one question: does life exist elsewhere in the universe? So where would we start our search for life outside our solar system? Well, the first thing you have to find is a habitable world. So that is a world where life can be sustained on its surface. And the technical definition that we use for a habitable world is a world that can maintain liquid water on its surface. And I know some people may be jumping up and down in their seats and saying, yes, yes, but aren't we going to look for life on Mars, and aren't we going to potentially look for life on Europa? Because there could be life in the subsurface of Mars, and there could be life in the oceans of Europa underneath a very thick ice cap. But remember, we're going to try and look for life around distant stars, so we do have to give ourselves a break. And so our definition is that it must have liquid water on its surface, so that we hope that there's lots of biomass, lots of life on its surface as well, which makes it easier to detect. Trying to detect life under 100 kilometers of ice 10 parsecs away is extremely difficult. So when we're doing the search for life outside our solar system, we tend to stick to this slightly limited definition of the habitable zone or a habitable planet, one that has liquid water on its surface. But there are many, many challenges in searching for these habitable worlds. First of all, we believe that habitable worlds are probably going to be terrestrial planets, that is, rocky planets roughly the size of the Earth. And these planets, in the visible at least, where we can see, don't give off their own light. That we must see them by the reflection of their star's light upon them. They're also very, very far away, which makes them very, very faint, which should never be underestimated. And even though they're very faint, which would be hard enough, they are also lost in the glare of their parent star. So when we're looking for these terrestrial planets around other stars, we have to do two things. One, we have to suppress the light coming from the star so it isn't blinding us to it, the faint little planet sitting next to it. And we also have to be able to separate the planet from the star so that we can see them as two distinct points of light, not just one glob. Two distinct points of light. But even when you manage to do that, and you need absolutely huge telescopes to separate the planet and the star, you're still going to have a point of light. Okay, as represented by my little blue square here. Okay, so when we find our planets around other stars, at least in the next 20 years or so, we won't have the technology to be able to spatially resolve that planet. That is, to be able to see details on its surface. So if you imagine our little blue dot there is an average of everything that planet really is. So if we take away the blue dot, you can see that what we're trying to do is learn about this wonderful complex world, which may have continents and oceans and life and clouds. Everything is in that dot. So everything we learn about it will be disk averaged. We won't be able to hone in on something that looks more interesting than anything else. We just get the whole lot averaged together. So the signs of life that we would look for on this planet must be a global phenomenon. They must cover a large fraction of the surface of the planet or be visible in the atmosphere of that planet. And remember, too, that our interpretation, our ability to tell if that planet is habitable, can support life, or if it's already inhabited, will only be as good as how far down into the atmosphere we can see. So that's another challenge. We may not see all the way to the surface if this thing is completely covered in clouds. But even though that dot looks a little bit discouraging, you'll notice that dot has a color. And so this is where it starts to get interesting. Even though we can't spatially resolve it, we will be able to take the light from that dot and break it up into its constituent colors, break it up into what we call a spectrum. And we'll be able to tell its color. We'll be able to tell if it's giving off more red light or more blue light. And the finer we can break up that spectrum, the better off we are, because we'll then be able to look for particular colors in the spectrum that there are less of or more of than we expect. And these will actually be signatures of what the planet's surface and atmosphere is like. So when we look at that planet, there will be all of these different processes that will be contributing to that spectrum of the planet that we're trying to get. And so here's a somewhat confusing diagram about all of the different things that we have to try and look for. We'll be looking for things like the chemistry of the atmosphere, what it's made of, the temperature and pressure structure that we see, whether there are volcanic gases and aerosols coming through, whether the atmosphere escapes over time, whether it's been enriched by impacts, and then finally we'll be looking for the impact of life on that planetary environment.